Welcome to Visual Algebra Lecture 4.9, External Semidirect Products and Holomorphs. We've previously seen how to construct semidirect products using our inflation method. In this lecture, we will formalize the construction of a semidirect product of two groups algebraically. That is, we'll pin down what the binary operation on the Cartesian product has to be. This is called an external semidirect product. An example of this is called the holomorph of a group, which is the semidirect product of a group with its automorphism group. We've actually seen a few examples of this already, including almost a full construction in the previous lecture. We will finish with the concept of an internal semidirect product, which is when a group is isomorphic to a semidirect product of two of its subgroups. That will be the subject of the following lecture. Let's get started. Thus far, we've seen how to construct a semidirect product of A with B using our so-called inflation method. Now, if you don't know what I'm talking about, you should first watch my video called Semidirect Products Intuitively back in Chapter 2. In this method, we take a group A, think A for automorphism, whose Cayley graph gets rewired, and a group B, whose nodes in the Cayley graph get blown up, so B for balloon. And then we stick in rewired copies of A into the nodes for B and connect them up accordingly. But in doing so, we have to label each inflated node with some automorphism to tell us which rewiring goes where. This is done by a labeling map, which is a holomorphism, that inputs the nodes of B, the balloons, and outputs the labels, which are automorphisms. See, I told you, if you haven't watched that video, you really should first. Naturally, this can be defined algebraically, and it typically is. To see how to do this, we will start with the direct product, which is the group on the underlying set A cross B. That's the Cartesian product. And recall that we multiply two elements, a1 comma b1 times a1 comma b2 as a1 a2 comma b1 b2. The external semidirect product of A with B via some labeling map theta is also on the same underlying set, A cross B. However, the binary operation is a little bit different. I'm going to use star and asterisk instead of a dot for this. It's defined as follows. A1 comma B1 star A2 comma B2 is the regular Cartesian product up here of A1 comma B1 with, well, instead of A2 B2, it's an automorphism applied to A2 with B2. So theta of B1, this is what label which automorphism is prescribed to node B1. We apply that to A2 comma B2. So formally, this is the ordered pair A1 theta of B1 of B2 comma B1 B2. And just to emphasize, I didn't put it in here, but it's assumed that because this is an automorphism, this whole thing is a function of A2. So these parentheses really should go here, but it's typically omitted because it's clear from the context what we mean. Now, we defined it like this, but really you can just hold this definition up into a mirror and put the B's first. So we could define a similar group on B cross A, just by swap the coordinates, and we will write that B semidirect product A. So if we do that, the open side of the symbol will point toward A, and we'll see why later. It's because A is normal. And we're still going to put the theta on the right-hand side. Now, I should mention that some books put the theta on the left-hand side when you swap sides, or some books have a different convention with which side is open, but I think this is the most common, and this is the one that we are going to use. Let's now compare and contrast the direct product with a semidirect product. This is the same example that I did back in that Chapter 2 lecture that I asked you to watch first. it's the direct product of C5 with C4. So you can think of C4 as being the group B. These are the balloons that get blown up. And so here are those balloons. Here are the nodes of C4. We blow up each of those balloons, and we're going to stick in an unrewired copy of C5 into each one. And then we just connect up corresponding pairs of vertices. So we originally had, maybe I should draw the original Cayley graph for B looked like this. So we just take each of these nodes and we blow them up into balloons like this, stick in those C5 copies, and then every time that we have an edge from one node to another, we connect up all corresponding pairs of nodes like this. Algebraically, A1 comma B1 times A2 comma B2, so A1 A2 comma B1 B2. We can write this without the parentheses, because A and B commute. We can write this just as A1 A2 times B1 B2. We will soon do this with the internal semidirect products that I told you about. And let's think of this in terms of paths. So we start from here, and we first follow the A1 path, say whatever that is, and then the B1 path, let's say that's down here, in either order. So red, blue equals blue, red here. And now we are at the A1 node in the B1 balloon. So I'm just doing 1, 1, but in general, this could be a general path and a general path here. So we're now at the A1 node in the B1 balloon. Once we're here, we follow the A2 path. Maybe that's red, red. And then the B2 path, maybe that's blue, blue, in either order. And that is the product A1, A2, B1, B2. Okay, got it? I'm going to do the same thing now, but I'm going to rewire some of these Cayley graphs. In the semidirect product of C5 with C4, well, this is one particular semidirect product. We saw that there were two in addition to the direct product back in chapter 2. We have we have rewired copies in each of these, and our labeling map is, remember that's a homomorphism, and that goes from B to the automorphism group of A, and that just labels each one of these nodes with a homomorphism. So if we're going to call this in the original group, if this was B to the 0, B to the first, B squared, B cubed, and this map can be thought of as just B to the I sent to theta to the I, where theta is generator of the automorphism group. So this is the generator of the automorphism group. Think of it as the doubling map. We double, each red arrow here is the doubling of one of these, and if we double twice, then that's the quadrupling map. We double 3 times, so if we double this, now that's just the tripling map. And now we double this, we're back to where we started, because that's multiplying by 6, which is 1 mod 5. So here, let's multiply A1 comma B1 times A2 comma B2. So we're going to, once again, follow the A1 and the B1 path in either order. So we'll say red, blue. Now, at this point, this is not rewired. So think of there being original Cayley graph down here. So we're at the A1 node in the B1 balloon. But now, at this point, we rewire this Cayley graph via this automorphism. And then we follow the A2 and the B2 path in either order to get over here. So it's the same basic property, just that the difference is that before we do the A2 path, we rewire that Cayley graph. Let's now prove something which we expect, is that the subgroup A cross the identity is normal in a semidirect product B. And I have the definition of multiplication here as a reminder, because it'll be useful to look at. So for this, how do we do this? We take an arbitrary element in here, and let's conjugate it by an element in here. So let's take some x comma 1 in A cross the identity, and conjugate by some element A comma B in the semidirect product. So let's do this. We get A comma B star X comma 1 star A comma B inverse. So let's do this first one first. And using our definition above, and let me emphasize that that's what we're going to do first. This is A times theta B X comma B. So that's, again, it's A times, instead of AX, it's A times some rewired copy X, and then B times 1 is in here. And so what I want you to notice is that since X is in A, and this is an automorphism of A, this thing is in A itself. So now we have this times A inverse comma B inverse, and we just use our definition once again. So we get A times theta B X, but now instead of multiplying by A inverse, we're going to multiply by some rewired copy. So theta B times A inverse. So let me stick this in here. This is theta B times A inverse. And then we just multiply. In the next coordinate, we do B times B inverse, which is just the identity. So let's put a 1 right there. So notice that each of these things, so this is in A, this is in A, and of course the little a is in A. So this entire thing is in A, and that's exactly what we had to show. This is in A cross the identity. So that's a check. I should put a box there. So that's that. I said this before, but let me write this out. Our notation is that, well, inspired by A cross B. When we have A cross B, both A and B are normal. And technically, when I say A and B, I really mean like A cross the identity and the identity cross B. So once again, I'm using the same 1 for the identity in both groups, just because I don't want to, death by subscript. So that's so that motivates when I have the notation A semidirect product B, and I have see how the open side of this resembles a direct product. And since both of these are open, I'm going to point the open thing to the normal factor. So A is normal in the entire group, and B is typically not. If B is, as we'll see, this is actually a direct product. So that's the inspiration for this notation. Again, it's not always used in this. We could do this whole construction and just swap the first and the second coordinates, as I said in the last slide, in which case we would get B and A, and A would be normal. So in that case, I will do something like this. And in both these cases, I'll put the subscript on the right-hand side. Here's a new definition, which made its way into the title of this lecture, and that is the holomorph of a group, denoted hol of G, is just the semidirect product of G with the automorphism group of G. And I should say a semidirect product, but it's a fairly canonical one, so I will omit the subscript. I guess it wouldn't hurt to put the subscript in here. And I should tell you what this labeling map is. Well, remember, the subscript generally goes from B to the automorphism group of A. So we label each big balloon with a rewiring of this. But now our B is the automorphism group of G, which is what A is. So there's a natural identity map that just sends some automorphism feed to itself. So if that happens, then the binary operation G1 comma alpha star G2 comma beta is just G1 times alpha of G2 comma alpha beta. Now I claim that you've seen this before. So anytime that I've had the automorphism group of a group, and I've stuck in copies of, or I've stuck in rewirings and connected things up, that was the holomorph. So here is the holomorph of C3 and C2. I guess normally what I do is I rewire the copies. Here I've fixed the position of the copies, and I put these blue edges here. This is from an example that we'll do in the next lecture. Here's an example that I think we've seen before. I also think I actually took this for the next lecture as well, but I'm sure we've seen stuff just like this before, where in both of these cases, the automorphism group of in this case C3 is isomorphic to C2. In this case, the automorphism group of C6. Remember, this is the things that are relative. This is isomorphic to U6. These are the things relatively prime to 6 under multiplication mod 6. And this is just consists of 1 and 5. So this is C2. So in both these cases, the automorphism group is just a size 2 group. So if we take the Cayley graph of C2, so say this is like 1 and this is B, and we blow up the nodes, we stick in rewired copies of A in here, connect things up, this is what we get. So this is where we stick in the identity rewiring into here, and here we stick in the non-trivial rewiring phi in here, and same thing over here, except again once I embedded them the same way, which ends up crossing the blue arrows instead of here where it does not cross the blue arrows. Let's do some more complicated examples, but I think these will actually be a little more familiar to you. So recall that the automorphism group of C5 is isomorphic to C4. So the holomorph of C5 is just a semidirect product of C5 with C4. And we've already seen this construction. Here is the Cayley graph of the automorphism group of C5, and in each node we stick in a rewired copy of C5. And then when we connect up everything, this is what we get. And this is particularly the affine general linear group. That is the 2 by 2 invertible matrices over Z5, which are affine transformations. And to quickly remember which one this is, I always forget, I had to check it myself. I know that there are 3 non-abelian groups of order 20. There's this one, there's D10, and then there's the dicyclic group, Dig10. And these two have an element of order 10, this one does not. And so if this group has an element of order 10, it's got to be in this coset. It can't be B squares. These things will all 4 have to have order 10. So I quickly just did, let's see, blue, blue, red, blue, blue, red. That has order 2. So that can't be either of these. It has to be that one. Again, we went over this in an earlier lecture. I encourage you to check that out. Here's an example of a holomorph that we just saw in a previous lecture. I think it was actually the last lecture on automorphisms. And now I say this is the first step of the construction. So the holomorph of V4, you take the automorphism group of V4 and you blow up the nodes. That's what we did. And then we stick in rewired copies of V4 into those. So we did this in detail. This was alpha. This is alpha squared. this was beta, this is alpha beta, and alpha squared beta. So we had all 6 rewirings on one slide, and then the next slide I did this Cayley graph and I stuck those rewirings in here. And I say it's the first step because this itself is not quite a Cayley graph of a group of what is this, order 24, but what we have to do is we have to actually connect up with this. So these orange edges here are really short for saying that we have to connect up all of these. And if we do that, then we get, and we will get a Cayley graph. It'll be kind of messy, so I'm typically not going to do this. But you get the basic idea. We also have to connect up all of the purple edges as well. Here's another example. Again, the first step of the holomorph of D3. So we, on one slide, did all 6 rewirings of D3. And then we took the automorphism group of D3, which is also D3, and we stuck those rewirings in here. And if we connect these things up, we will have a semidirect product of D3 with itself, which is the holomorph of D3. So stay tuned in a bit. This thing, surprisingly, is also isomorphic to the product, a direct product of D3 with D3, which is not in any way obvious. But on the next slide, I hope to convince you, or at least give an outline for why this should be true. One important thing that I want to point out in this lecture, because it will be one of the key ideas in the following lecture, is that in the semidirect product of A and B, the subgroups, I'm going to call them A and B, I really mean A cross the identity and the identity cross B, have the following 3 properties. They generate the entire semidirect product. In other words, I can write every ordered pair as a product of something in here with something in here, even with that twisted definition along an automorphism. So it looks like this. These intersect trivially, and one of them, that is A cross the identity, is normal. In the next lecture, we'll see that anytime we have a group with 2 subgroups N and H that generate G, intersect trivially, and one of them is normal, then we have a semidirect product. So G is actually isomorphic to the semidirect product of these 2. And that begs the question, what is the automorphism? And that is an inner automorphism. So it's a thing that maps every element in H, let's call it H, to a particular, to just conjugating by H. So the inner automorphism that conjugates by H is, so it sends N to H and H inverse. So that's the labeling map. And this is called an inner or an internal semidirect product. I like the word internal because it's contrasting with external semidirect product, which is this what we've been seeing in this lecture. But I get the term inner too, because this is an inner automorphism. And sometimes if people who call this inner, they will call the external semidirect product the outer semidirect product, which I'm not as much of a fan of because it doesn't actually involve outer automorphisms. But a nice thing about this is that this condition up here, these conditions can easily be checked in the subgroup lattice by inspection. So for example, if we have a group G and we have a normal subgroup N and a non-normal subgroup H, so N is only conjugate to itself, H might be in a larger conjugate class, and these things intersect trivially, so they intersect trivially and they generate G, then we know that G is isomorphic to a semidirect product of N with H along some automorphism, along an inner automorphism. And it turns out, so we'll prove this in the next lecture, but we'll also see a lot of examples with actual subgroup lattices. But some groups break up as semidirect products in multiple ways. We'll actually see one of order 12 that breaks up into a semidirect product 3 different ways and a direct product. So sometimes we can also find a pair of groups that satisfy this condition that are both normal. And one example of that, well, let me just say, I've said that D6 is isomorphic to semidirect product of C6 and C2, but also of D3 with C2. So you can find pairs of subgroups in here. I'll let you think about that satisfy these conditions. And in here, this one's normal, that one's not, and here both of these are normal. But back to something I mentioned in the previous lecture, or the previous slide, sorry, about holomorph. So if we have a group, D3 was one of these examples, but in general, suppose that we have the holomorph of G, which is the semidirect product of G with the automorphism group of G. And let's suppose that the center is trivial. So what that means is, that in particular G mod the center is isomorphic to the inner automorphism group. Remember that? So that means that every element in G gives rise to a unique inner automorphism. So suppose that the center is trivial, but also suppose that the outer automorphism group of G is trivial as well. So suppose that both of these conditions hold. So in other words, the inner, so that just means, remember, the outer automorphism group is the full automorphism group mod the inner automorphism group. So all that is saying is that suppose that the inner automorphism group is equal to the entire automorphism group. If this happens, I think G is called complete when this happens. I claim that this holomorph is actually isomorphic to G cross G, the direct product of G with itself. And why this works is because we can find, in this case, we can find two copies of the subgroup G inside here that are both normal. One of them is this first factor right here, G cross the identity, so that's normal. But also the other one is the so-called diagonal subgroup. So elements in the automorphism group, if are precisely inner automorphisms, so they have the form phi G. So this subgroup here, G comma phi G, is isomorphic to G, and it is normal, and it intersects trivially with, so I'm going to call this one B, and I'm going to call this one, or maybe I should call this one N and H. A is G comma the trivial automorphism, which is isomorphic to G. So in this case, these things are both normal. They intersect trivially. They generate everything. So the holomorph is isomorphic to G cross G. And that's why in the previous slide, we saw that the holomorph of D3, which is D3 semidirect product, the automorphism group, which is D3, is also isomorphic to the direct product of D3 with D3. Okay, so in the next lecture, we will explore this. This is, again, the internal semidirect product. We'll prove it, and we'll see a lot of examples within subgroup lattices. It's one of those important skills that we will be using throughout the class. So make sure that you don't miss it. I'll see you then.